Hello, this is Nicholas from Silicon Chip Publications, and today I'd like to talk to you about the March 2026 issue of Silicon Chip, which is going on sale very soon, probably around the time this video is released. Now, here's the cover. We have a few things featured on the cover: solar panel protector and optimizer, DCC booster, graphing thermometer, all of which we'll look at, plus a few more of the major articles. We won't look at everything in the magazine. But turning now to the contents page, we can see we have the second part of our three-part history of Intel series, and this is going to talk about from the early 1990s, like the time of the 286, 386 through to now, the developments at Intel. Then we have part 5 of our power electronics series, which talks about things like DC AC conversion, AC DC conversion, DC DC conversion, power factor correction. This issue, it's dealing with power factor correction and electromagnetic interference suppression, which are important topics for power electronics. Then we have a review of some self-powered wireless switches, which are quite interesting devices. They have no battery. They derive the power from you actually pressing them, and they transmit wireless signals. That's pretty cool. Then we have wiring up a new home. So it's a somewhat unusual article, but quite a useful one if you're building a house, with some advice on how you should go about it, because obviously it's much easier to run wires while the house is being built than after it's built. Depends on the construction, but especially with things like double brick, once it's finished, it's very hard to get wires through it. Then we have 4 projects: the solar panel protector. The solar panel protector does 2 basic things. One is it reduces the chance of damage from lightning. Now, obviously, if the panels are struck directly by lightning, there's nothing it can do. But a lot of the time, things are damaged by lightning that doesn't actually strike it. It might strike the ground nearby, or a tree or a pole, and it's actually the induced current that does damage. So this will help protect against that. And it also has an ideal diode function, which means that if some panels are in shade and some aren't, it will allow the ones that are not in shade to continue producing power. We have a DCC booster project. This is part of a series. We've had a DCC decoder and a DCC base station and a remote controller for the base station. And the nice thing about this, not only is this a booster, it can also operate as a reverse loop controller or even a simple base station. Then we have the construction part of our internet radio project, which is based on a Raspberry Pi and a graphing thermometer. And one of the nice things about that is it's a very simple circuit, but still quite useful. And then we have some other things in the magazine: Circuit Notebook, which I'm not going to go into detail; Serviceman's Log we'll have a look at; Vintage Radio we'll have a look at. We also have Mailbag and Ask Silicon Chip. I won't look at those. Turning now to the first feature, History of Intel Part 2. It starts here, we're talking about the Pentium, which was pretty much a revolutionary processor at the time, although interestingly, AMD and others were actually producing similar processors. There was a real competition back then, as there is today. Here's a block diagram of the Pentium and some pictures of the actual chips. Pentium 2, Pentium 3, Pentium 4, Itanium. And then we start to talking about the core processors, which are the more modern Intel chips, also Atom. There's been a lot of, well, about 20 different core processor generations. So here's a table that shows some of the differences and when they were introduced and so on, and talking about the new system of tiles and so on. So the third part, in the April issue, will talk more about what Intel has planned for the future. So this is basically bringing it up to the 2020s. Moving on now to the solar panel protector, which is the next article in the magazine. As I mentioned, it reduces the chance of damage from lightning, and it also has that ideal diode function. You can see that he's built 3 protectors here and mounted them in his caravan, I believe it is. Here's the circuit, which is relatively straightforward, and it uses these ICs that are specifically for the ideal diode function with an external MOSFET, plus some power supply circuitry and some varistors for lightning protection. There's the board. It shows you how to install the components. There's the one he's actually built and wired up, and there's some information here about wiring. It's a pretty straightforward project. Definitely worth installing if you have a small solar system, like an off-grid system, something like that. And then if we look at the next article, now we're onto the power electronics, and we're talking about buck converters, so a step-down converter, and how to analyze it, where the current flows during each stage. And now we're looking at some filtering, so basically trying to stop switching artifacts, current and voltage from feeding back into the mains or whatever's powering it, because there are limits on how much noise you can inject into the mains. And it's actually a fairly complicated topic. It isn't just a matter of whacking a filter on there. it has to be designed correctly for the specific application. Here's an example of a very common type of mains EMI filter using a common mode choke and 3 capacitors, 1 class X capacitor and 2 class Y capacitors. And we talk a bit about how to select those components. And now we're talking about power factor correction. So basically trying to make a switch mode power supply's current draw sinusoidal rather than just drawing at the peaks of the mains waveform, and how we do it, and the sort of the feedback loops used in the different topologies. And here's an example of it. Here's a real power factor correction circuit, a demonstration board you can buy, and here's the circuit for it. And as you can see, it looks fairly complicated, but really there isn't all that much to it. You have your basic EMI filter here, and then a MOSFET with a couple of there's a transformer and an inductor, and then some feedback networks and a controller chip, and that does the power factor correction. And we talk about compensating it, and an actual scope grab showing an example, and you can see how the current draw waveform matches the voltage waveform pretty closely. So that gives you a very high power factor of 0.96. Moving on now to the DCC booster and reverse loop controller. So this is a much smaller unit than our base station, but it can actually act as a base station. Obviously, it's a little bit less capable because you have a smaller screen and fewer controls and so on, but it will do the job. But more importantly, it can be connected to our base station and act as a booster. So in other words, if the base station can supply 10 amps and you need 20 amps, well, you can add a booster to run a separate section of track so that can deliver another 10 amps. And as a reverse loop controller, it can drive that separate section of tracks and reverse the polarity if necessary. So here's the circuit of the booster and reverse loop controller. Relatively straightforward. There's a microcontroller, 2 motor drivers driving the tracks, power supply, a few other bits and pieces for communications. That's about it really. Oh, and there's a screen there, which is optional. If you're just using it as a booster, you don't need to install the screen. It's really only if you want to use it as a base station. Here's the assembled prototype. On both sides, you can see the motor drivers and the microcontroller on the back there. And this socket is for connecting to a remote control. There's the finished unit, and when we talk here about why you need a reverse loop controller, so if you have this loop, you have a train going around it, it has to reverse the polarity before it goes all the way around, or else it's going to short out, because this blue track starts connecting to the red, but it ends connecting to the black. So it has to swap, and this reverse loop controller will do that automatically and seamlessly. There's how to assemble the board, where the components go on both sides, how to make the cutouts in the box, and then we talk about actually using it, some of the different modes and screens and so on, and how to wire it up to the base station. There's the parts list, and that's pretty much it. And then we can look at the self-powered wireless switches. So these are little modules that you can buy, and you can see there the coils, and there's a magnet, and basically when you push the switch, the magnet induces current in the coils, which powers up this board and transmits some signals, some coded signals. There's the circuit. This is specialized chip, which harvests energy from the switch as well as doing the RF oscillator and modulation and so on. You can power it externally if you want to, if you have a battery or something like that, but you don't need it. Here are some examples of how it generates the power to run itself. Here's a slightly different version with 2 coils, and here's the actual received data at the other end. You can see it gets 2.5 full sequences from one press of the button. And this is very handy in a location, an outdoor location, where you know there's no power and you don't want to have to replace the battery constantly. And we give some examples of receivers that you can use to pick up these signals, and there's also example software we provide. So if we can look at the next article now, this is about wiring up houses, not just for power, but also for data and audio and stuff like that. So we talk about, well, here's a dimmer, running HDMI throughout the house, running speaker cables, the cheapest way to get speaker cable, talking about where to put things in a new house. These brush plates are pretty interesting. They let you just run any cable that you want. And we also talk about converting things HDMI to RF signal to run over coaxial cable, which is a good way to do it. Basically, if you're renovating or building a house, it's worth reading this to get some ideas of what you might need to do. Now we have our internet radio part 2. So the part 1 described how this thing works, showed some of the circuit, but now we're actually going to explain how to build it. So it's 3D printed. You can download and print the files, and then this talks about connecting the modules together, wiring it up. There's a little bit of a trick there. you do need to wire it up correctly if you want to get good sound quality. So you follow this wiring diagram, and this shows all the components mounted on the 3D printed case and everything wired together, and then it makes a neat little package. And then setting up the software, free software, which is based on Linux, and you can run VLC on it or other audio video playback software. So that's a nice little project there for somebody who has a 3D printer. And now we can look at the graphing thermometer. As I said, it's very simple but useful. So it uses a thermocouple. You can see the parts list is pretty short. The circuit is pretty small. It's just an 8-pin microcontroller, an LCD screen, a boost module, a thermocouple, which is just basically a special kind of wire with forms a temperature sensor on the end, plus a few buttons and resistors, and that's pretty much it. So here you can see everything on the board. There isn't much to it, and yet it will display a graph of the temperature over a period that you can adjust, and it will handle quite a wide range of temperatures, up to several hundred degrees. It's powered by a single 1.5 volt cell, which is quite handy. Here are some examples of temperature plots. That looks like a refill soldering temperature profile. Advice on programming the chip. So it's a nice simple project and a useful one. Then we have Serviceman's Log, which has some stories about repairing stuff. He was talking about repairing a dishwasher, where apparently there was a reed switch based flow sensor that had failed, which wasn't obvious, and luckily it was easy to fix once he found it. Repairing radio on a boat, repairing a Breville microwave where the fan had failed, and fixing an inverter for a turntable that was actually built from a project in the magazine, but one of the parts was no good. And then a toaster repair and a stereo receiver, which is one of the more complicated things that is fixed. Mainly just, I think the screen backlight had failed, and also the radio tuner section had some bad components. And then moving on to Vintage Radio, the last major article I'm going to talk about. This is an interesting old radio from 1927, so just under 100 years old. It almost looks like a toolbox, but of course radios back then were very simple affairs. You can see in the circuit there's not much more to it than several valves and transformers. And there's the power supply. You can see how they've mounted the valves basically on a piece of wood, wired it up. This interesting multiple capacitor package that they came up with, quite unusual today. Some of the details of the wire wound resistors and tuning wheel, and then he talks about the frequency response and a matching speaker that came with it, or like that you could get with it, which used an unusual rocking armature mechanism that you would never see today. Today, very unusual set. Back then, I guess it was more common to build things this way. It's interesting to see how these things were done. So that's it for the March issue. Well, there's more in the March issue. There's Circuit Notebook and Mailbag and our Silicon Chip, but that's all the major articles. Quite a few interesting ones there, I think. So that should be on sale late February. Thanks for listening.